Intro music. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Earl Bellinger with us today. Hey, Earl.
Hi, Frank. Really happy to be here. This is really exciting for me. So,
Well, great. It's a really lovely APJ letter article. So happy
thank
to
you.
talk
Thank you.
about it. And of course, it's kind of interesting, right? Because rarely do we get a chance to talk about our actual articles, right? So you'll give talks and you'll cut out, figures from your papers, but you're packaging a little bit differently than if you're actually really talking about the paper itself. So I'm happy to be doing this where people can actually talk about the article that they spend so much time getting through. So it's great. Earl, where are you at? What's your geolocation?
I am in Aarhus, Denmark. So it's the second largest city in Denmark after Copenhagen, of course. And I'm at the Stellar Astrophysics Center, which is one of the Danish centers of excellence. And you're in Arizona?
I am in Phoenix, Arizona, and we will hit our first 100-degree Fahrenheit. So our first 35, 36 C here in a couple of days. So we will clear that barrier, and then we know that the power switch has been turned.
That sounds terrible. I'm really sorry for that.
Actually, okay. It's a pretty dry heat. I know people say that, but the humidity is really quite low. And so 90 to 100 is actually quite pleasant. Actually, I find it pleasant.
Yeah, I don't know if it's ever been that hot here in Denmark before. Of course, I'm not from Denmark, but I'm pretty sure we had a super summer a couple of years ago.
Yeah,
but it didn't get anywhere near 100.
Okay. Yeah, and I would. What's the general humidity like in Denmark?
I wish I knew off the top of my head, but I don't. It's pleasant. It's always kind of nice. I mean, it's the thing that's remarkable or notable is that you either have super long hours in the summer or super short hours in the winter. I mean, it's dark all winter. You only get a few hours of daylight in the winter.
Very cool.
Yeah.
But so it's perfectly fine in Phoenix for me when it gets to 100. 115, 120 is just hot, period.
Oh my gosh, I can't even imagine.
But it's like other places I've lived where in the winter you're primarily going to be indoors. In the summer you get out. Here it's the inverse of that. So in the summer you're primarily going to be indoors, and any other time you kind of get out. So it all balances in the end. That's a really awesome pillow over your right shoulder. That red
Thank you.
silver pillow.
Yeah.
Is that a pillow?
It's a pillow, yeah, and basically you can write anything you want in it. So my fiance made a star for us. You can, it's one of those that they turn over, so it's you change the red and the white.
Oh, very nice.
Like
maybe she's got a little business going there. I'll buy one.
Yeah, right.
Very cool. Cool. So Earl, what do you like to do for research?
Well, I work in the exciting field of astroseismology, so the study of pulsating stars, and try to use the information of those pulsations to understand what's going on inside of the star. And yeah, I love this field. I've been working on it since I was essentially a bachelor's student. Even though I studied computer science in college, I got onto a research project working on variable stars. And I just fell in love with it. And that was more than 10 years ago. And so I work on various types of pulsating stars. My main type of star that I look at are solar-like stars. So not necessarily the sun itself, although it is an interesting object, but other sun-like stars which exhibit a full spectrum of oscillations.
Mm-hmm.
And yeah, I try to use that information to infer conditions about the interior of the star and its evolutionary history. And from that, the world's your oyster. There are many there are many applications.
That is awesome. That is awesome. Very cool. And that'll bring us to this very lovely off the beaten track APJ letter. Asteroseismic constraints on the cosmic time variation of the gravitational constant from an ancient main sequence star. And Earl, take us away.
Yeah, absolutely. Thanks a lot. So, this is something that I think studies like this, I was really excited to be able to work on this because this is the kind of thing that got me excited about science in the first place. These sort of, I guess we could call it exotic physics.
Mhm.
The idea that the gravitational constant can vary goes back nearly 100 years. In the introduction, I cite Dirac, but there was actually interest even before Dirac, but his work is the main motivation why people essentially take this stuff sort of seriously. And but even before Dirac, there were people who were working on theories of modified gravity, where the gravitational constant is promoted to a variable. It's funny that we call it the gravitational constant because
Mhm.
it's possible that it's not actually constant. So the first interest in a variable gravitational constant were people basically reacting to or rejecting Einstein's theory of general relativity and trying to explain it within the Newtonian framework of just having a variable g and seeing how far you can get with that. And one of the major players in this kind of game, maybe not directly working on variable g, but this kind of stuff was Eddington. And Eddington is a little bit of a science hero of mine. Of course, there's a million things that are named after Eddington, but at the end of his life, he kind of went a little bit crazy. I'm not sure if you know this story, but he started working on the fundamental theory, where he tried to see like how can you explain the values of the dimensionless quantities we have in nature.
Right.
And he thought he could prove from first principles, for example, that the fine structure constant was 1 over 137.
Mhm.
And along with that, Dirac noticed that the gravitational constant goes with 1 over the age of the universe. And so people started working on theories of cosmology to explain how that could happen. And there were a multitude of theories that arose. One of them that's fairly famous is the Brans-Dicke theory, where you take general relativity and you just make g a variable that can vary over space and time. And but now in modern times, we have things like string theory, which also promote g to a variable quantity. And in particular, there was a paper on superstring theory, which actually predicted an amount that G can change over time. Um, and so, of course, a number of experiments have arisen to try to investigate this and try to determine whether G really does change. And so, the best constraint comes from solar system dynamics. Way back in 1962, some researchers shined a laser at the moon and then recorded the light travel time.
Mhm.
And essentially from that you get the distance, but you can also work out the dynamics of how the moon is changing in its orbit and so on. And from that you obtain extremely tight constraints on how G has changed over the past, I guess, five or six decades. But of course, if G is changing, it's probably changing over cosmological timescales, not over human lifetime. So while that constraint is extremely interesting and very important, it may not be probing the time in the universe where the actual changes to G were transpiring. Of course, there were other recent changes to G that have been suggested. I don't think I cite it here, but there was a paper that claimed, well, they didn't seriously claim it, but they pointed out that the measurements of G can be explained with a sinusoidal variation over time. Because different experiments on G have yielded different measurements over
Oh.
the past century.
Mhm.
But what they said was probably the instrumentation techniques have just, essentially gone awry a little bit, and that caused some kind of variation. In any case, there's been a large. Sorry, what's that?
Cool.
Yeah, right.
Very good.
Yeah, that is fun. Um, yeah, there's been a wide variety of experiments that have tried to measure the variation of G. So we have from the moon, we also have from the MESSENGER probe.
Yep.
There's also been the Viking landers on Mars. they also did a ranging experiment with lasers. And then you have yeah, some more exotic things. Let's say like you can get constraints from binary star systems, like neutron stars in a binary.
Sure.
And you can get constraints from white dwarfs and from globular clusters by fitting evolutionary models to them, and much in a similar way that I'll discuss how we do it here. And then you have constraints from Big Bang nucleosynthesis and from the cosmic microwave background. And all of these different experiments tend to give the same result, which is that G is constant insofar as we can measure it, but the limit at which we can measure it keeps kind of getting pushed more and more. It's always something of the order of a part per trillion per year of change is the upper bound that these different experiments yeah can put on the change of G.
Mm-hmm.
And yeah, so it's an interesting problem, and if such a change could be measured, that would be interesting for the future of theories of modified gravity. You know, what's going to come after general relativity? If string theory replaces it or some other theory, you know, I don't know if you have a favorite. Uh,
Oh no.
no skin in the game.
No.
That's fair. Yeah, I wouldn't personally also conjecture a replacement. I mean, they're fun to think about. There's like
They are.
quantum loop gravity and other such exotic things, but I have no idea which is the favorable theory on any grounds. But what's great is when these theories produce a prediction that we can then try to grapple with using
Indeed.
stuff that we think we understand more. Sorry, what did you say?
Yes.
Yeah. Okay. Indeed. Okay. So I was very happy to try to throw my what's the phrase? Throw my hat in the ring, or
Uh-huh. That's the phrase.
whatever people say. Yeah. And so basically, my work builds off of some results um, from Lawrence Krauss and Pierre Demarque and Gunther, who showed that the sun can be used as a laboratory for measuring the change in G over time. And that's because if the strength of gravity was stronger or weaker in the past, then the sun would have evolved under stronger or weaker gravity, and that would have a result on its structure, and that would consequently affect its present day structure when G is the value that we observe it to be, and so its oscillation frequencies would change.
Yes.
And so and yeah, what's interesting is you can obtain these kinds of constraints just by doing a dimensional analysis of stellar structure equations. That's what Teller did in 1948. So Teller was taking Dirac's idea very seriously, and what he said was that if G was different in the past, this could actually present some problems for the geological evolution of the Earth, because if G had changed by so much, he showed that the Earth would be inhospitable to life in the time span where we knew there was life on Earth. So this is related to the faint young sun problem.
Yep.
But actually, George Gamow of nucleosynthesis fame came out with, I think, one of his last papers before he passed away, saying that Teller's argument was valid insofar as the derivation was all correct, but he didn't consider how changes to some parameters could make the Earth survive. And so yeah, the sun is an interesting laboratory for that, and it's not in any apparent contradiction with the temperature of the Earth. So what I looked at was this star KIC 797074, and this is a really interesting star because this is a solar-like star, but it's among the lowest masses of stars that were observed by the Kepler mission that were seen to oscillate. And so Yeah, a brief reminder about the Kepler mission. Kepler stared at one fixed field of view in the sky for 4 straight years. And approximately once per minute, it took a measurement of a whole bunch of stars. And this is one of the stars that got this special treatment, essentially. And from that, we got to observe an extremely rich spectrum of oscillations, something of the order of 40 individual oscillation mode frequencies come out. And what's really nice about the star is that we've studied it a few times in previous studies, and not only is it fairly low mass, it has about 70% the mass of the sun, but it's also very old. It's almost 11 billion years old. So in contrast, the sun is 4.5 billion years old. So in terms of probing the changes to G over cosmic time, this star probes more than twice the amount of time than the sun probes.
Good. Okay.
Yes. Okay. And yeah, if we scroll now a little bit. So the first thing we did was essentially see how a variable gravitational constant will affect the theoretical evolution of a star. So that's what we see here in figure 1. So this is the same star, or the same, mock star, theoretical star. And we put in the same input parameters, so a mass of 0.75 of the solar mass and a low metallicity of 0.001. And then we changed this parameter beta. Now there's an equation in here which shows so beta controls the rate of change of the gravitational constant. And all it does is it says how strong or weak gravity was in the past. So it's a way of parameterizing this change. And so what you can see in this diagram is that essentially what you can see is that spectroscopy is not going to be able to resolve differences in G, because typical uncertainty and temperature for this type of star is 50 to 100 Kelvin. But the change you can see in the temperature is much smaller than that. And so, yeah, essentially, we need a different mechanism to try to resolve changes.
Okay.
But if you then go to figure 2, now we get to the good stuff. This is asteroseismology. So this is what asteroseismology can do for this problem. So this will take some explanation, because everyone's familiar with the HR diagram, but many people are not familiar with the asteroseismic HR diagram. So on the x-axis here, we have the large frequency separation. So when we look at a star like the sun, for example, we see the spectrum of oscillation modes. The sun is oscillating in a superposition of a great number of modes simultaneously. And a large number of those modes are radial modes. They're the entire sun basically expanding and collapsing, but in various shells. So the frequency of these different radial oscillation modes are separated by a nearly constant value, and that's called the large frequency separation. So the difference in successive radial mode frequencies in the sun is about 135 microhertz. And yeah, a characteristic frequency in the sun is about 3,000 microhertz. That's a period of 5 minutes. So the sun experiences 5-minute oscillations. Now, the large frequency separation we can measure to about 0.1 microhertz, or maybe 1 microhertz, depending on the star. And so that has great diagnostic potential. The large frequency separation turns out to be related to the mean density of the star. If you get its large frequency separation, you can almost immediately deduce its mean density. And of course, if you have additional information, you can then get the mass and the radius and other such things. The small separation, on the other hand, that's the difference in frequency between these radial mode oscillations. And so radial mode oscillations have a spherical degree of 0. Right next to radial mode oscillations in the oscillation spectrum are L of 2 modes. So they're not dipolar, but quadrupolar oscillation modes. And it turns out that this difference in frequency between radial mode frequencies and quadrupole frequencies, that is a sensitive instrument which measures the sound speed gradient in the core. Now, that statement on its face doesn't seem so powerful, but it turns out that the sound speed gradient is related to the mean molecular weight. The mean molecular weight is related to the abundance of helium. The abundance of helium is then the age on the main sequence, because of course the sun is converting hydrogen to helium over billions of years. And so if you can measure the amount of helium in the tank, you know its main sequence age. Fantastic. So small frequency separation gives you the age, and the large frequency separation gives you the mean density.
Okay.
Small frequency separation you can also measure to sub-microhertz precision, which means in this diagram, for those same changes that we saw to beta, to the amount the gravitational constant changes over time, we then can actually separate these tracks with astroseismic measurements.
Yep. Very clear. Nice separation there. Okay.
So for this particular star, you can see the typical uncertainty. I wrote it just below there. So you can see delta nu, we measure it to 0.06 microhertz, and the small separation we measure to 0.16 microhertz. And that's clearly, that clearly can define a space on this diagram. So that's fantastic. I mean, these preliminary calculations basically told us that we would be able to derive a constraint by modeling this star. What else is there to know? Well, it has a temperature of 5,300 Kelvin. That's fine. It's a little bit metal poor with an Fe on H of negative 0.5. And yeah, there's also nu max, which is sort of a characteristic frequency. And basically, these measurements tell us, if you're into solar type astroseismology, even just from looking at this, this is an old star that's on the main sequence and low mass. You get that straight away. And those measurements have been confirmed by detailed modeling fits, including what we proceed to do in this paper. So yes, interrupt me at any time, of course, if
I'm good. I'm with you.
Okay, great. Okay, so equation 2 shows how we parameterize the change in the gravitational constant over time. And this is essentially what's used in all the other works that have tried to investigate this. And so you say that we have the value of G that we observe right now, that's G naught, and we have whatever uncertainty associated with it. But we want to say that G changes over time, and so we have the age of the universe, and then we have the time that's elapsed, since then. And this beta controls how G changes. So it's just a simple power law. It's an ad hoc parameterization. One could also use a linear approximation. You got to do something, and so that's essentially what people have done. And so we opted to do the same thing in lieu of a these theories don't seem to produce a functional form, and so this is a way to parameterize it and derive a constraint.
Uh-huh.
And so what do we want to do? What we want to do is model this star by calculating theoretical evolution of a star, and then the theoretical oscillations of those theoretical models, and match them up to the observed data. And from that, you can constrain its mass, its age, its initial chemistry, and the time variation of the gravitational constant, because this beta is one of those free parameters.
Yeah.
We can look at the first table, which is just above, I think.
Uh-huh. Bonk.
Yes. So here are the priors that we put on our modeling for this star. So we say we're going to look at betas that span from negative 0.2 to 0.2. And that was essentially chosen because that corresponds with some of the lower bounds that other experiments find. So in order to try to improve on those constraints, I mean, the other experiments have already bound it by that much. We don't adopt any of their measurements as a prior, but we adopt the bounds from their measurements.
Okay.
And then we have the age of the star, which has to go between 0 and the age of the universe.
Yes.
That's hopefully clear enough prior. We have the mass of the star. We just set it uniformly between 0.5 and 1. I should mention that it's of benefit that this is a low mass star because we avoid some of the theoretical uncertainties that are associated with modeling some higher mass astroseismic targets.
Mm.
You have effects like convective core overshooting. We might have needed to parameterize that, but it has no convective core. And you have things like diffusion. You might need more interesting physics like radiative levitation and so on. If you have a higher mass star, it will counteract those effects. So we can calculate diffusion without necessarily needing to worry that we're in a parameter space where it could be problematic for our model.
Yeah.
And then we also vary the initial helium abundance and initial metallicity. And yeah, frequently in solar-like astroseismology, people couple these together. For example, you assume a galactic chemical evolution law, but here we've completely decoupled them. So they're totally free to vary. And then finally, we have the mixing length parameter, which controls the efficiency of convection. And so on top of that, we actually also incorporate the uncertainties on nuclear reaction rates. So that's in table 2. It should be, I think, in the same location on the next page.
Indeed.
Oh, okay, yeah. Yeah, so there was a paper from Alfio Bonanno, I hope I pronounced that correctly. He updated Gunther's work on the gravitational constant variation being measured from helioseismology, from solar data. And he was able to show that that it's somewhat degenerate with this first reaction, the first PP reaction rate. And so he suggested propagating through the uncertainty on that nuclear reaction rate. And I thought, since we're already there, let's propagate through the other reaction rate uncertainties as well.
Yep.
So we adopted these priors from this Adelberger paper, and we essentially found that with these priors, we aren't able to improve the constraints based on this one star, but we should return back to that when we talk about future work at the end, because that's an interesting possibility. But yeah, that's just to say that we also propagated through these uncertainties. So now when we think about the free parameters we have in this fit, we have the mass, age, initial helium abundance, initial metallicity, mixing length parameter, the change to the gravitational constant. We have a prior on the age of the universe, and then we have 5 nuclear reaction rates. So I think that gets us up to 12 parameters.
Yes.
I remember hoping that it was going to come out to 11 dimensions, because that would have been a funny coincidence with string theory. but our hopes don't dictate the scientific direction we should go in. So anyway, what we want to do is then do this Bayesian modeling. And on the previous page, we had the equations, but probably everyone knows Bayes formula, so I won't belabor the point. But the whole idea is then that we have to define a likelihood function, and we've just gone through our priors. So the likelihood function is now based on these astroseismic frequency ratios, which you can see in equation 4. So what's the deal with these? So naively, a person would think you have a model of a star and you calculate its frequencies, so just look at how the frequencies compare between the model and the star. But for stars like the sun, we have this issue called the surface term, which is the fact that our models don't correctly reproduce the surface properties of these stars. And so this imposes some shifts in the theoretical frequencies, which makes them not directly comparable to the observed frequencies.
Right.
And there are a couple ways to mitigate this. There's the Bollinger 2016 surface term, where you can fit and subtract off the differences in frequency imposed by the surface term. But there's also this treatment that Ian Roxburgh and Sergei Vorontsov came up with in 2003. And what they were able to show is that if you take the ratios of different frequencies
Okay.
and the differences of those frequencies. And this R10 is like a 5-point average. They were able to show on theoretical grounds that this subtracts off the outer layer of the model. And so they put in different surface terms into the model, and you get the same ratios, even though they have completely different frequencies.
Okay.
So this is now a widely used prescription for getting surface term independent measurements of or diagnostics of the interior structure of the star. And so, yeah, one can then form these ratios and try to see whether or not your models match those. And so our likelihood function is built off of trying to match those astroseismic frequency ratios.
Okay.
And so, yeah, I did this experiment both with the MESA stellar evolution code and with the Aztec stellar evolution code. Aztec being the Aarhus stellar evolution code made by Jørn Christensen Dausko. And we decided to report the Aztec results in this paper. So yeah, what we did was we put in different parameters for the for this star, and then evolved it to that age with those parameters, calculated the ratios according to that model, compared those to the observations, and then got a goodness of fit, a likelihood. And we repeated this using Markov chain Monte Carlo, so MCMC. And we did it until the chains converged, and it took 100,000 iterations, which took a month and a half on our supercomputing cluster to generate these 100,000 stellar evolution tracks.
Okay.
And from that, we were able to derive constraints on the parameters of this star and on the cosmic time variation of the gravitational constant. And so our results are summarized. You can see on the right side of the screen. For the star, we get out an age of approximately 11 billion years, which is pretty cool. This is truly an ancient star. This is one of the oldest stars in the galaxy. We also find that it's a very low mass star. Its mass is about 72% the mass of the sun. It has a pretty low helium abundance, but its helium abundance is greater than the primordial helium abundance that we get from, for example, Big Bang nucleosynthesis, which gives about 0.2463. So with 0.252, we're quite in the clear there. It's a low metallicity, which is somewhat reassuring because cosmologists tell us that the initial stars should have low metallicity. And yeah, the mixing length parameter is nearly solar, which might be expected. And then finally, we get the big result that we were after, which is how much has the gravitational constant changed? And so we can see this in this equation 7 in the bottom left corner. We can simply take this beta that we derive and the T naught, which is the age of the universe. We propagate its uncertainties and do this Bayesian Asteroseismic estimate. And one simply needs to take the ratio of these two quantities, and we get the rate of change of G over G. And we find that it changes by no more than about 1 part in a trillion per year. And we can see this also in the histogram, which is the figure 3. Yes, so if we marginalize over all of the samples in our MCMC simulation, so 100,000 samples, we can then see the posterior probability of all of these changes to the gravitational constant. And we find that here, we find this dashed line where it changes from blue to orange. That's I think it's the 95% upper bound on the rate of change to the gravitational constant. So just over five parts in a trillion per year. And so there you go. As far as we can tell, there's no astroseismic evidence for a variable gravitational constant. And so so far, astroseismology supports general relativity and does not yet provide empirical evidence for string theory.
Very cool. Very cool. Very nice. Very nice. Well, Earl, thank you very much for walking us through that really lovely APJ letter. And so
My pleasure.
Since you mentioned a little bit, let's aim toward the future a little bit. Are there other stars, low mass stars, either with Kepler or with TESS, or perhaps with forthcoming Plato mission that could be used to tighten these constraints, let's say by another order of magnitude or so, or just in general, where do we go with using seismology for cosmology over the next 5 years?
Absolutely. Yeah. So that's something I'm very interested in pursuing further. So to tighten this constraint, one can imagine adding more stars to the analysis. And this becomes really difficult, actually, because when you model these stars, you want to have each of the stars have their own parameters in terms of their mass and their age and so on, but you want them to share this value of the gravitational constant, which means you're not independently modeling these stars, you're modeling them all together. So each star then contributes an additional, let's say, 5 dimensions to the sampling problem. And so the complexity explodes really quickly.
Right.
To get an order of magnitude constraint, one can imagine probably the error goes up, goes down roughly with the square root of the number of objects that you add. And so to go down by a factor 10, you need 100 more stars. And so it gets really difficult really quickly, because 100 stars, that's then 500 more parameters. And so you're doing a lot of sampling. Yep. Sorry, what did you say?
Yes, cursive dimensionality.
Yeah. So it gets really tricky really quickly. So this is something I'm actively looking into. And there's a lot of techniques that we can try to employ to speed this up and bring down the dimensionality. And so that's hopefully something on the horizon, how we can I'm calling it simultaneous astroseismology, where you fit stars independently, but you share some aspects of their fitting. So that's something to look out for on the horizon. The other thing that could be possible is, beyond the interest of a variable gravitational constant, there are other shared parameters in here. And so I mentioned the nuclear reaction rates. It would also be interesting to try to combine the data from various stars to try to bring down some uncertainties on these nuclear reaction rates. It may be possible to derive asteroseismic constraints on nuclear reaction rates. And that would be a very fun thing to look into. And that I've started working on that as well. It would be, yeah.
Very nice.
And another aspect, so I'm really in love with this idea of astroseismology offering things to other fields of astrophysics. And it has a really rich history, right? I mean, you can think about Cepheids being used as a cosmic yardstick. What was it? Edwin Hubble destroyed I'm getting his name wrong. The famous astronomer Shapir, I can't remember, but he destroyed his universe. He gave him this letter showing that he had discovered a Cepheid in Andromeda, and so it was clearly outside of the Milky Way, and that helped settle the great debate in astronomy 100 years ago. But then, more recently, astroseismology has been really useful for exoplanetary science, for providing masses and radii of host stars, which then gives you very precise constraints on masses and radii of exoplanets, and also the ages of those systems. And then you also have things like galactic archaeology, so uncovering how our galaxy evolved over time. Well, you need ages of stars for that. So astroseismology is really useful. Well, in terms of exotic physics, like the variation of the gravitational constant, one can also imagine the variation in the fine structure constant. And it turns out that comes in through stellar evolution calculations as well, through the screening term in nuclear reactions. And so, that it may one day be possible to also obtain astroseismic constraints on alpha as well, which would be an interesting thing to do.
Presumably you won't get exactly 137.
Yeah, right. Adding tables would be
Integer
so sad.
value, integer value. Very good. Very cool. Earl, thank you so much for walking us through this. And I think there's a lot of bright applications coming in the near future.
Thank you so much for having me on here. This is really, really a great experience for me.
Cool. All right, everyone. Thank you very much. And we'll see you on the next one. Bye-bye.